to have Gregoire to come speak to us. She's an academic research fellow at Leeds University. She completed her PhD at Bristol on the Northern Hemisphere climate and ice sheets during the glaciation. Yes, is that it?
That's true.
And she's currently working on modeling ice sheets and marine ice sheet instability and things like that. And she'll be giving a talk today on sea level changes and abrupt climate change. And yes, I will give the floor to you.
Thank you.
Two actually small announcements before I let you speak. If you are one of our DTP students, we do have a sign-up sheet for you to tell Grantham that you're here, so do sign, please. And we will have a small drink reception at the end, so do stay on if you can, and we'll have a chat, and it'll be great. Yeah, that's it. Thank you.
Thanks. Well, thank you very much for the invitation. It's a pleasure to be here. It's my first time here, actually, so I think it's a fantastic campus. So what I want to talk to you about today is a view from the past about abrupt climate change and rapid sea level changes. So what can we really learn from the past? Before I start, I'd like to acknowledge my main collaborators and contributors to this work. There's lots of names missing from this, but really I want to point out Ruja Vanovic, who's done a lot of the climate modeling that I'm going to show, and also Ilka Matera, Niall Gandhi, two PhD students that I supervise who've done part of this work. James Salter and Daniel Williamson are also two statisticians that I collaborate with currently. So, we'll start by giving a bit of background on why should we be interested in what happened in the past in terms of climate change and sea level change. I thought I'd just show these figures. The one on the left is from the IPCC Assessment Report 5, so 2013 now. And this was their best assessment or projections of future changes in sea level under several scenarios of CO2 emissions, so this RCP 8.5, which is the higher end, and a 2.6 is the lower end. All right, so it gives us a bracket of, or a way to have an idea of how sea level might change in the future. One thing to note is that this is including all contributions to sea level change. And in the next century, this is a lot, mainly coming from thermal expansion of the ocean due to warming, our greenhouse gas emissions, and glaciers. And then there's, I think, something like a quarter, maybe, that is from ice sheets, Greenland and Antarctica. But one thing to note is that in this IPCC report, they couldn't give us a higher end of plausible sea level change. And we had only medium confidence in these projections. And the reason is that there is a possibility that there are mechanisms that could produce much larger sea level changes and rates of sea level rise in the future. And currently, we don't have a good grasp on these. So I'm going to touch upon some of these. And the plot on the right is another projection of change in sea level, again in the next century. And note that these scales are slightly different. So this one goes up to 1 meter, this one goes up to 1.5 meters. So already this projection on the right is for a larger sea level change by 2100. It's from a paper by DeConto and Pollard, so more recent. What's interesting about it is that it looked at the past, periods mainly the last interglacial and the Pliocene, 3 million years ago, to learn and calibrate and train their model, and then apply this model to the future. So this is an estimate of future sea level change based on what we know from the past. And what the main thing from their study was that they introduced a new mechanism, a possible mechanism for an even bigger sea level change in the future. And this is what's called ice cliff mechanism. Note here that this is only the contribution from Antarctica, which was only a quarter of this. So if you add the thermal expansion, the glaciers on top of that, we're looking at much larger rates of sea level change in the future. So I'm not going to say very much about this study or debate whether I think they were right or wrong. Probably stay away from this. Actually, there was a lot of debate around this paper. Really what I think is interesting is that it's an example of using the past to try and understand our world better. And what's happened in this case is that studying the past has actually lowered our confidence in this projection. Right, so we're learning more, but actually we're learning that we know less. And the uncertainties in future sea level change shouldn't be this, but should be much larger. And in fact, we don't know how the high-end possibility of sea level change. So I think this is one of the main things that we've learned by studying past climate and sea level change, is that we learn that we tend to be a little bit too confident in our projection of future climate change just based on present observations. So the period I'm going to present here and mostly talk about is the last deglaciation. This is my favorite period to study. This is the transition out of the last ice age. So starting from about 21 to 23,000 years ago, a period of relative climate stability, really cold, it's called the last glacial maximum. We had large ice sheets. This animation is going to show us. In fact, this is the Holocene, so the interglacial period we're in. And here we're back to this last glacial maximum, large ice sheet covering the whole of Canada and large parts of northern Europe. We had a British and Irish ice sheet as well, which I'm going to mention as well in a minute. What happened then? So this is a major transition, a major climate change that's taken us out of the last ice age. And what happened is that we had natural variabilities in the orbit of the Earth causing an increase in the energy received on the Earth at the latitude of these large northern hemisphere ice sheets. And this is what drove their retreat, and it was followed by an increase in CO2. Interestingly, the latest records of CO2 show some really rapid jumps of CO2, and this is degassing from the oceans. What's also interesting is to look at the changes in sea level during that time, and obviously we had some major changes in sea level because of these ice sheets disappearing. But we see that the changes in sea level aren't really following the drivers, so the change in insolation and the change in greenhouse gases, but we have some period of acceleration of sea level change. And those are the kind of things that I'm interested to look at. The climate also didn't evolve very smoothly, and in fact here is the Greenland record from reconstructed temperature from ice core records, and in grey is an equivalent record from Antarctica, and showing that, well, in Greenland we have some major abrupt warmings and cooling, and they are actually seen elsewhere in the northern hemisphere. In Antarctica, it's not exactly the same picture. So we have this warming when the north is keeping cool. So there's lots of interesting abrupt climate changes and abrupt sea level changes that we don't fully understand. So here's what I'm going to talk about and focus on today. I'm going to give you examples of mechanisms of ice sheet instability. So what kind of mechanisms can cause rapid changes in the ice sheets that lead to rapid sea level change. We're going to talk about marine ice sheet instability, which is the major threat for future sea level, focusing on the British ice sheet. I'm going to show you some instabilities due to surface mass balance, so not necessarily. So this first instability is due to the dynamics of the ice sheet, and the second one is due to the accumulation and melt of ice at the surface. We're going to then look at how acceleration in the melt of these ice sheets can cause major impact on ocean circulation and climate, looking at two specific events in the past. And then hopefully I'll have enough time at the end to tell you a little bit more about, well, we'll ask the question, can we actually predict those instabilities? And how might we go about understanding what could trigger them, or in fact, really looking at the uncertainties in those processes. So I'll start off with marine ice sheet instability, but before that, for those who aren't too familiar with ice sheets and how they operate, here's a little bit of a 101 on ice sheets. So there's a very simple diagram showing you a typical ice sheet that might be, in fact you might see this part here on the left as being a little bit like the Greenland ice sheet, and this part on the right as being a lot like the Antarctic ice sheet. So what we have is snow accumulating over very, very long periods of time. So we're talking about hundreds of thousands of years. And usually the center of these ice sheets so cold that there's never any melt. All we have is just accumulation of snow. Snow compacts to form ice. And then ice flows under its own weight towards the edges of the ice sheet. And then we lose this ice either through what we called ablation at the surface of the ice sheet. This is melt, essentially. And this is typically how the Greenland ice sheet operates. There's melt on the surface of the ice sheet. In Antarctica, there's hardly any melt on the surface of the ice sheet, and the ice flows all the way towards the ocean to form these ice shelves. And then we either have melt underneath the ice shelves because of the influence of the ocean, and warm waters that might come underneath these ice shelves and enhance the melt, or we have some calving into icebergs, and we every so often have on the news some events of major calving of very large icebergs. So we've had you know some very impressively big icebergs. I think one the size of London recently, carving off Antarctica. So what's marine ice sheet instability then? You might have heard about it maybe on the news. This is a mechanism that's relatively recent, actually. It's, we're still trying to understand these mechanisms and understand how to model it. And it's currently the largest threat for future sea level change. This could produce a major change in sea level in the future. So we're really trying to grasp the sort of magnitude of the changes that could happen. The mechanism is the following. So you've got an ice sheet here, like on Antarctica, ending up in an ice shelf. This is the ocean. It's carving off. And we might have some warm water entering under this ice shelf, producing larger melt than usual. Here you've got what we call the grounding line, which is a transition between the ice that's grounded, well, it's grounded below sea level, but it is resting on the ground, and the ice shelf that's floating ice. So that transition is called the grounding line. And that's really important because the flux, so the discharge of ice, the flux of ice at the grounding line is essentially reflecting how much ice is lost from the ice sheet. And it's dependent on the thickness of ice at the grounding line, so that's been shown theoretically quite recently. So what happens is if we have more warm waters arriving under the ice shelf, it might induce a retreat of this grounding line. And if we're sitting on a reverse slope, so sloping towards the interior of the ice sheet, if the grounding line retreats, then the thickness at the grounding line is going to increase, which means the flow out of the ice sheet is going to increase, and we're going to kick in a runaway effect, in essence. So this is the principle behind this ice sheet instability. It's been shown recently that it's quite technically difficult to simulate properly this instability, and you need very high resolution in numerical models. So resolution of the order of hundreds of meters. And it's very challenging to have a model that operates at hundreds of meters there at the grounding line and in the rest of the ice sheet. Antarctica is a big continent. But thankfully, we have a model that's been developed exactly for this purpose, which is called bicycles. You can see a representation of it here on the right. This is, I think this is the Amazon Sea Pine Island Glacier, so it is parts of West Antarctica being represented here. And what this model is able to do is refine automatically its resolution where it's needed, so specifically at the grounding line or even in ice streams where we like to have higher resolution. But the interior of the ice sheets, where not very much happens, is very slow moving ice, then we can have resolution of the orders of 8 kilometers, for example, so 8 kilometer grid box. So this is some work that Niall Gandhi, who I supervise for his PhD project, has been working on. He's associated with a project called British Chrono. So British Chrono has been working very hard in the last 4 years to reconstruct the retreat of the British ice sheet. So I told you earlier that during the last ice age, our country, or large parts of our country, was covered in ice. Not so far as London, and actually almost as far as Leeds, but Niall likes to say that Leeds would have been a terminal university at the last glacial maximum. So we take our students half an hour away on the train and they can see areas covered in ice during that period. So we now, thanks to this British Chrono project, have amazing constraints on the rates of retreat of the ice sheets. And parts of the aim of this project was to provide constraints for models, like this one, so we can test their ability to simulate past ice sheet changes. We're not quite there yet, the project's still ongoing, but what we're doing now is starting to model this ice sheet and comparing our results with data and seeing what happened. So because this ice sheet was marine terminating at the start of the last deglaciation, and it then transitioned onto just resting on the ground, so not terminating in the ocean. There's some hypothesis that this would have affected the rate of retreat, so we can have a look at things like marine ice sheet instability and how that controlled the retreat of this ice sheet. So here's some very recent results from Niall. I'll try and move out of the way. So he's currently preparing his publication. He's showing here, so what Niall did is a very simple simulation to start with. We have a very cold climate where the ice sheet is at equilibrium at its maximum extent. He's compared it to the available reconstructions. And then he ramps up the temperature by 1.5 degrees. So he tries to kick in a retreat of the ice sheet in a very simple way. And he's focusing on this area first, because it's where we have an incredible amount of data showing some really interesting behaviours. So this is what we call the Minch area in northern Scotland. So he's simulating a retreat of the ice sheets, but interestingly, even though he's just adding a 1.5 degrees warming constant throughout his experiment, he doesn't really have a linear retreat. He has quite a fast retreat to start with, and then some stability, and then an acceleration again. And this is what it looks like. Unfortunately, you can't really see the contours, but here you can see this Isle of Lewis here, and this is mainland. So at this stage, ice has retreated, but it's no longer terminating in the ocean. So it's retreated on land. But in between, you can see here how it evolves from this stage to here when it's really stabilized in between these two land masses, and then it's retreating again, and then we've got an acceleration between here and here. Something happens that produced a really rapid acceleration of the retreats. Could this be an instability like the one I've mentioned before? So looking a bit closer, you can see the same thing. Those lines here are the maximum extent of the ice sheets. You can see it at 500 years through his simulation. So you can see those line bunching up here. So as we enter this area here, we almost have more stability in the ice sheet. And later on here, there's a big acceleration just when the ice sheet really goes past this point. And this point here happens to be quite a higher elevation than the rest. And here we have this reverse slope that I mentioned earlier. So what we're seeing here is an example of marine ice sheet instability. So it's this reverse slope which is producing an acceleration in the retreat of the ice sheet once it goes past this point. So we have here in the British ice sheet some evidence of marine ice sheet instability. So there's lots of data coming out, and we're hoping that constraints on the timing of the retreat and pace of the retreat at different stages could help us maybe test our model or even calibrate it or improve the representation of processes within it. There was a question of whether these changes could be reversible. Again, that's a way to really test whether this is an instability. So what Niall's done is at regular intervals, he's taken the sort of extent as a starting point and then reversed the temperature to cold conditions and see if the ice regrows to its full extent. And it does until it reaches a threshold here. So it either recovers to a full extent like this, or it actually just goes to a collapsed state here. And this is when the grounding line goes past this point, so almost like a point of no return, when it's gone on that reverse slope. So this is an interesting occurrence of this marine ice sheet instability in the past, and we're hoping continuing this work can help us test our models and improve them. Now there's some other types of instabilities that can occur when the ice sheet is not terminating in the ocean, but is just sitting on a continent. In the case of Greenland ice sheet today, but in the past this would have been the Northern Hemisphere, the North American ice sheet, for example. So I'm going to show you some work and how I go about modeling this ice sheet to try and understand those possible instabilities. So this is essentially very similar to what Niall was doing, a little bit more sophisticated maybe. We're using an ice sheet model here that's simpler than bicycles. It's faster, it doesn't have the ability to refine its resolution. So in terms of dynamics, there's a lot of approximations. It cannot simulate marine ice sheet instability, but we can look at the evolution of ice sheets, and especially the surface mass balance of the ice sheet over longer periods of times and on the scale of whole continents. So here is an image of the ice sheet thickness at the last glacial maximum, and you can recognize Greenland here, and here the whole of Canada is covered in ice. So we can simulate this ice sheet over the whole of the last glacial cycle, so the growth of the ice sheet and the retreat. So what I do is to simulate the mass balance of the ice sheet, I take information from complex climate models, so general circulation models, like the ones that are used for the IPCC, or what tends to happen is older versions. So we've got one called Trace 21K. It's run with the CCSM3 model. So that was a model that was used in the AR4, the assessment report for the IPCC. And there's another model which you can see here in black. It's called FAMOUS. It's a fast general circulation model. So what we've done is half the resolution of the model. And this is so we can run very long climate simulations with it. So we can simulate the whole of the last glaciation. So 20,000 year long simulations with a general circulation model. And remember that these models are typically used for the next couple of centuries. And it's already challenging to model this length of time. So here it's an incredible amount of computer time and data that goes into this work trying to simulate the transient evolution of climate over this whole period. And the way it's done is that we impose evolution of greenhouse gases like I've shown initially. So we had degassing from the oceans, increasing greenhouse gases concentration in the atmosphere. We also have some changes in orbit. And because it takes so long to run these climate models, we have to make some assumptions about the ice sheet evolution within them. So we use reconstructions of this. So this plot here is showing you the evolution over time of temperature in Greenland. And green is the reconstruction from an ice core. Remember showing you this abrupt warming, abrupt cooling. And this simulation in black from the famous climate model actually doesn't simulate any of these large changes. We don't have any of the initial cold period, and we don't have this abrupt warming or this return to cold condition later on. But what we have is a simulation of the overall temperature change between this cold period and the warmer period. So we can learn still from this. If we use this climate data to force the ice sheet model, here's our best simulation, if you like. This is the evolution of volume over the North American ice sheet through the deglaciation. You can see it going down. This is data points in diameter reconstruction. Essentially, lots of uncertainty on this. A little bit less uncertainty on the area of the ice sheet, actually. But you can see this model matches this fairly well. What's interesting here is these two accelerations in the melt from the ice sheets. And we can see it here also in the volume changes. So remember, here our climate forcing was very smooth. So we only have a progressive warming through this period, and yet we do have these two occurrences of what are called meltwater pulses, accelerations in the melt. The first one is here, and it happens in the model when these two ice sheet domes separate. So we've got an ice sheet sitting on the Rocky Mountains called the Cordilleran ice sheet, and one on the rest of the continent called the Laurentide ice sheet, and it's the separation of these two ice sheets which causes this increase in melt. If we take a sort of transect through, we can try and understand a little bit more what happens. And here you can see the surface of the ice sheet. So this is what is calling the Cordilleran ice sheet on the Rocky Mountains. You see the mountains here. And this is the edge of the Laurentide ice sheet. In between is what I call the saddle, but it's a little bit like a mountain pass made of ice, and it sits at lower elevation. And this mechanism is triggered when we start having some melt at the surface in this region. And remember, this is a transect through here, but if melt is occurring here, it means there are large parts of the ice sheets that are suddenly susceptible to melt. And this is just because of progressive warming of the ice sheet. Once this happens, melt increases at the surface of the ice sheet. Oh, because if the surface melts, we're losing ice, so it's going to lower. And at lower elevation, it gets warmer, so the melt increases that way. So it's a feedback between the surface mass balance, the melt, and the elevation. And this is a very simple concept. What's specific here is that it happens when we have two ice sheet domes and they separate from each other. So it's another example of instability in the ice sheet, but this time just due to the surface mass balance. So we've related this first event to something that really happened, and we see in the sea level record, called the Meltwater Pulse 1A. And our reasons for doing this is that this separation between the Cordilleran and the Laurentide ice sheet happened in reality. We know it happened. There was an opening of this, what we call the ice-free corridor between the two ice sheets. Actually hypothesized that this was a migration route for big mammals and maybe humans. There's some debate about that, but it could be the case. So there's been some interest in dating this, and we think it happened around 15 to 14,000 years ago. And this happened to coincide with the timing of a very large sea level rise, rapid sea level rise, that we see in sea level records, such as the one from Tahiti. And this is what you see here. This was recorded as 12 to 22 meters of sea level change in 340 years or less. So that's quite large. I remember the initial projection I showed for the future of the order of magnitudes of 1 meter in 100 years. So this is much larger than that. The largest sea level change we've recorded in the past. And there seems to be some correspondence between the two, so this mechanism could be responsible, maybe not for all of this sea level change, but a large parts of it, maybe half of it. So we were interested in understanding the consequences of this event, and this is some work that was led by Ruja Ivanovic. So what we did is first ask our colleague Andy Wickett to calculate where the melt would be going, where is it rooted. So what you see on this image on the continents are drainage basins, and is calculated from topography and changes in topography in the past. And the colors here are showing the ice sheets and where we have a loss of ice, so where we have the main melt. So this is melt in between the Coriolanan ice sheet and the Laurentide ice sheet, and you can see that large parts of it go into the Arctic, and some will go either through the Mississippi or maybe the Hudson River, which is just here. So there's about half going either way. What you can see in the ocean, and those colors are representing the change in salinity due to this large amount of meltwater entering the ocean. So you can see much lower salinity in the Arctic and generally in the whole of the North Atlantic. So how does that affect ocean circulation and climate? Yes. So the plot on the left at the top here is showing the change in surface air temperature as a consequence of this melt of the ice sheet, this instability in the ice sheets. And you can see some cooling in the northern hemisphere and some more warming in the southern hemisphere. And this is a typical, what we call bipolar seesaw, which occurs as a consequence of a slowdown in the Atlantic meridional overturning circulation. So has any of you seen The Day After Tomorrow? Yeah, I see. This is essentially what was depicted in The Day After Tomorrow. And in fact, I think it was the 8.2 kilo event that I'm going to mention in a little bit. So essentially a slowdown of the overturning circulation, potentially due to melt of the Greenland ice sheets, and causing some very dramatic and very rapid changes in climate in this film. It may be a little bit overdone, but I do like the film because it's one of the rare Hollywood movies where the hero is a paleoclimatologist. Quite good, I recommend it. So this is what's happening here, major climate change as a consequence of this. Now we have a lot of uncertainty on when this instability, when this saddle collapse could have occurred. Essentially because the separation of the Cordilleran and Laurentide ice sheet is not very well dated. I told you it was probably between 15 and 14,000 years ago. But actually I have some colleagues that would suggest that it might have been around 16,000 years ago. So here in this diagram we're looking at temperature in Greenland, again from the same Greenland ice core, where you have this rapid boiling warming. And this separation of the two ice sheets could either have occurred maybe after this abrupt warming, and we're going to see a little bit later why, or maybe before. And so this pattern of cooling could explain some of these wiggles, if you like, in this record, but we're not really sure which yet. It's hard for now to reconcile the sequence of events. One easier event, though, is the second meltwater pulse that I've showed you earlier, which happens later on in the glaciation. In our simulation, it happens between 10 and 7.5 thousand years ago. And this time, so this is plots from the ice sheets model I showed, and you have three domes around Hudson Bay. You can see the contours, you can see it better here, the contours of Hudson Bay today. And these three domes get separated from each other. And it's this, again, saddle collapse mechanisms that explain an acceleration of melt around 9,000 to 8,000 years ago. This happens to coincide with the timing of an event called the 8.2 kiloyear event. So 8,200 years ago, and if we look at, again, Greenland records, actually several of them, but this time goes from right to left. In paleoclimatology, we can't decide whether time should go from left to right or right to left. Anyway, in this case, it goes from there. And you can see this major blip, I guess, in a very stable climate. So this is a proxy for temperature change. And if you zoom in, it's about 160-year-long cooling that is 3 degrees in Greenland. You can see the same cooling in different places around the Northern Hemisphere. In Europe, for example, it's about 1 to 1.5 degrees. And you can see it also in the North Atlantic. This event was traditionally thought to be due to the release, the abrupt outburst of Lake Agassiz in Ojibwe, which used to be held behind the North American ice sheet. And as the ice sheet opened, it let a way for these very large volume of water to be suddenly released. The problem is that our models don't simulate a cooling of more than a couple of decades, really, from just a very short outburst of a lake. So what we suggested instead is that it is this sort of melt from the ice sheets over a century which could have caused the 8.2 kiloyear event. And this is work done by Ilka Matero and published last year, where he modeled a cooling from 100-year or 200-year long acceleration in melt from the ice sheets. And he was able, and you can see here at the top, to reproduce the temperature change in Greenland and other places where we have data, not only the magnitude of the change, but the duration. So what's interesting here is that this event could actually be used to test the sensitivity of ocean circulation in complex climate models. Because we're starting to have a good idea of what caused the event, how much melt could have been coming from the ice sheet, and we have some constraints on the surface climate change. So now I want to tell you a little bit. I'll first ask you a question. Do you think we can predict those instabilities? So I'd argue that it's really hard to predict instabilities because any little change or any little error in the climate that would have caused these retreats would affect the timing and the magnitude of these events. But what we can do is use some statistical methods to run ensembles of experiments to evaluate the range of plausible behaviors of these instabilities, when they might occur, how large would the sea level change be. And also we can ask questions like, could they have been triggered by something, like another event? And for example, I mentioned a really abrupt warming in the northern hemisphere called the boiling warming. And in Greenland, it's recorded as 14 degrees of temperature change. And most of this happens within a matter of decades. So it's major abrupt climate change. I'll admit it, we don't fully understand how this happened. We know it's probably related to some resumption of ocean circulation, but why this occurred is still puzzling to us. Interestingly, in 2012, Deschamps and colleagues found this abrupt or rapid sea level change called the meltwater pulse 1A, that I've mentioned before, probably occurred just after this abrupt warming. So there's a question, could this abrupt warming have somehow caused the rapid sea level change, or even triggered the saddle collapse instability that I mentioned before. So to investigate this, I collaborated with Betty Otter-Bliesner, who was involved in running this simulation shown in red here. So this was with the CCSM3 general circulation model. It took about 2 years for them to run the simulation. And interestingly, they simulated an abrupt warming that looks a lot like this bowling alley road warming. They might have simulated it for the wrong reason. But here I'm mostly interested in the fact that it looks to be roughly the right pace of warming and the right amplitude, not just in Greenland, but actually in other places around the world. So I've used this as another way to drive changes in my model. And then we can explore the uncertainties by varying model parameters that either relate to ice sheet dynamics or ice sheet mass balance, and run hundreds and hundreds of experiments. I can then compare the outputs from these simulations with some ground truthing geological records. And we have some very good constraints on the maximum extent of the ice sheets and how it retreated through the deglaciation. This is a map of the extent at 13,000 years ago, and you can see the opening of this corridor here. Well, the corridor had already opened. And all of this data, all these points are constraints where we know at that time there was no ice. And I can compare this reconstruction with my model here. It shows a discrepancy with one of the simulations. So there's either too much ice or too little ice. And I can do this in a systematic way to really chuck out a lot of the simulations that aren't right. So this is my ensemble of simulations. I'm going to skip a little bit over. Interestingly, so if I take the simulations that compare well with the data, and here are the ones only produced with this abrupt warming, I can have a look, 350 years following the abrupt warming, how much sea level rise do we have? And then this is the distribution. And you can see here two modes. We either have something around 4 meters, or we can have something up to 6 meters sea level rise in 340 years. And interestingly, in those simulations, what happens is that the saddle collapse, this separation between the Cortland and Laurentide ice sheet, happens just after the abrupt warming. So we have cases, and this is an example. This is actually the top end scenario. So following this abrupt warming, we lose a lot of ice here in this saddle. So the warming is triggering the instability and potentially causing here 6 meters of sea level rise. So this could have happened and could have explained large parts of meltwater pulse 1A. So it's an example where an instability can be triggered by an abrupt climate change. But there's another possibility that we can't rule out, is that the separation of the two ice sheets happened before the abrupt warming, in which case the abrupt warming still produces some sea level rise, but much lower, only 3 to 4 meters. If I've got a little bit more time, yeah, I'll go on to talk about most recent work I've been involved in, which was funded as part of the Past Earth Network. Have I got? Yes. So the Past Earth Network was funded by EPSRC and meant to bring together statisticians and paleoclimatologists together. And part of our aims were to try and help constrain uncertainties in the models, and there were other parts of the project which were constraining uncertainties in the data. And this was just a 6-month feasibility study, and we managed to do quite a lot of work during that time, really thanks to James Salter, who did a lot of the statistical work on this. So really our challenge was that what I showed you so far, we're able to sample uncertainty in parameters in our models, right? So parameters that might control the dynamics or the surface mass balance, the numbers, right, that we don't have a good handle on. So we can do that very well, what we can't do is sample the uncertainty in the climate, because climate varies in time and space. So we've got 3D maps of temperatures and precipitation. But climate is the largest source of uncertainty in this work. Partly because we have biases in our models, even for the models used to simulating the next 100 years have got large biases, especially at the high latitudes. In some of these models, you'd be growing an ice sheet on Alaska today, just because it's too cold and there's snow around all year long. So large biases, especially at the high latitude, but also these models are really expensive to run. And remember, one of these simulations took 2 years to run. So they were able to do a handful of simulations, but they couldn't really vary on certain parameters within them, or even the uncertain inputs like the timing of CO2 increase. Weren't able to do this. So we need another way to be able to sample the uncertainty in the climate, and this is what we're trying to get at. So I told you large biases in the models. This is a handful, so 15 or 16 simulations available over that period. One of them is this Trace 21K with abrupt warming. The others are done with the famous climate models. So the fast version of the model. And with that model, we were able to run 15 simulations, varying model parameters. But you can see systematically all of these simulations are way too cold in Alaska compared to reconstructions of past climate change. In Greenland, it's better agreements, but really a lot of these simulations don't produce the abrupt warmings or the coolings. So what we wanted to do is somehow combine information from these models and from these reconstructions of past climate change in a statistical manner. So we have data available at all these locations. Actually, there's even more records available, but because we only had 6 months, we had to focus on just a few, well, as many as we could. So we took a spread over the world and all the records we could find around North America. So our aim was really to build a statistical model of temperature change through the last deglaciation based on the models and which match the proxy records of temperature change. So we did this. I'm not going to go into the details because I don't have time. But we essentially decomposed the patterns of climate change in the models, in that ensemble of 16 models, both in time and space. And this is some examples of temporal evolution of climate change. It doesn't match the records, but it's just a decomposition of this temporal evolution of climate change. You can see this abrupt warming here that's seen in some of these models, and then some cooling periods. So we decompose this in time and in space. These some examples of how the temperature might vary through space in some of these simulations. We put it all together, and we have some temporal climate change decomposition, some spatial climate change decomposition, put it all together with over a mean of the ensemble. And then we have coefficients that we can sample very efficiently to try and match the observations are shown within their uncertainty. And through this method, James produced initially 500 sets of climate evolution which match observations within uncertainty, and that were based on these models. And here they are. So these are all in gray. The models are in blue, data in red in the case of Greenland, Alaska, and North America. And in gray, we suddenly have evolution of climate that match the data better, but also gives us an uncertainty around that data. So that's what we're trying to get at. We can then feed it into an ice sheet model, and this is the evolution of ice volume through the deglaciation. Gray is the initial ensemble of 500 simulations we ran, and then we were able to use this information to even refine the climate inputs. So we use constraints on the ice sheet extent to get at a more refined range of climate change. And these are the blue and yellow curves. And eventually, if we look at the simulations which match evolution or constraints on ice volume, we get maybe 10 or 20 simulations. And we can then average those and look at the ice extent in those simulations. This is at the last glacial maximum. Red is reconstruction of ice extent, and we have a fairly good match. Later on, through the deglaciation, we start seeing issues here, for example, too much ice or not enough in some places. So we do have some work yet to do to refine this, this methodology. For example, the areas where we have a mismatch between the model and the data, a systematic mismatch, because we haven't allowed for enough uncertainty in the climate forcing. So we need to further refine this method. But I think these first steps really demonstrate that it is feasible to use these kinds of methods to sample uncertainty in the climate. And we've used it through the last deglaciation, but there would be some possibility of once we've tested it on the past, to potentially apply it to future climate change. So I'm going to end here. I've told you through this last 45 minutes, 50 minutes, about several mechanisms of instabilities in the ice sheet. One called the marine ice sheet instability, and we've seen some evidence of this in the British ice sheet. We've also talked about some instabilities caused by a surface mass balance of these ice sheets that could have related to meltwater pulse 1A, the largest sea level rise that we've seen in the past, and the 8.2 kilo event. And we've seen how this large amount of water entering the oceans can slow down overturning circulation and cause cooling. And finally, we can run ensembles of simulations by collaborating with statisticians to try and evaluate the plausible triggers of these instabilities, but also the possible timings, amplitudes, and duration of the resulting sea level change. So, thank you very much.
Thank you very much, Lauren, for this talk. We have some time for questions, so do ask.
Yes? Hi.
My name is Charlotte Littlehurst, and I'm from an organisation called China Dialogue, which reports on environmental issues in China and here. And so I'm a journalist, and I'm very interested in how you help people grasp the magnitude of the changes that are happening that you described in your talk. And we're very interested in the IPCC report that's coming out later this year. I think there's still a lot of controversy around that and concern that it doesn't go far enough in its projections. And I was just wondering what slide from today's presentation, or what one case study you would use to show people how fast things are changing and how much depends on the climate and the uncertainties that are not known.
Okay, so that's a very interesting question. So one of the main challenges in grasping the impact of sea level change is that number of meters of sea level change in, say, 100 years is understanding how that relates to coastal changes. So there are some tools to actually see from, a certain number of meters of sea level change how the coast change, and I haven't actually shown very much of these kinds of things. I guess what I think is interesting from the past is to contrast the rates of projection of sea level change in the future to what happens in the maximum changes of sea level that we've seen. I think meltwater pulse 1A is an interesting comparison to that. But actually, I would argue that from this work, we're suggesting that a lot of meltwater pulse 1A came from the North American ice sheet. That is no longer here. And so that's actually quite reassuring in that you need a very large ice sheet that is already melting a lot to produce these very rapid and large rates of sea level change in the past. So even though we kind of can see those evidence of very rapid sea level change in the past, doesn't mean that this could happen in the next century. So it's a little bit of a reassuring thing. Does that help?
Yeah, it does.
Okay.
Yeah, it's nice to have a more positive
Yeah.
take on it.
We often focus on the negatives or the the very sort of dramatic consequences, but I think in this case it's a little bit reassuring. Okay. Yes, so I can say a little bit about this. So essentially, what happens in Antarctica is, especially in parts of West Antarctica, there are places with this reverse slope. So they've been shown that a couple of glaciers would be susceptible to marine ice sheet instability. And so what happens is, if you, in a model, in a hypothetical world, if you do induce a warming, you have a retreat. And if you reverse this warming, you might not actually get a reverse because of this instability. It's harder to produce an advance. So you kind of need to have further cooling than the initial conditions to get there. In the case of the British ice sheet, for example, well, it did get to its maximum extent somehow. So, and we could explain that by the fact that there was some variability in the climate, so there must have been some colder condition that allow the ice sheet to progress past this point of reversibility in our simulations. Does that make sense? Yeah. So that's the point about an instability is it's harder to go one way than the other. You kind of need to pull back even harder. And I mean, this has implications for, let's say, the future of the Greenland ice sheets. And it's been suggested that the saddle collapse instability, for example, could occur in Greenland because the northern parts of the ice sheet and the southern part could separate from each other. This will not happen in the next century, I can reassure you, but it may happen within a couple of thousand years. And if we go past this point, it will be much harder to regrow the Greenland ice sheet. So there's some legacy to our current greenhouse gas emissions, and we may not get back to how the Earth is currently for maybe tens of thousands of years. Does that answer the question? Yeah.
How accurate do you measure the grounding line currently? How many of the grounding lines have you mapped to the 8 kilometres
of resolution? So it can be done using remote sensing, the satellites. What happens is that the ice that's floating, its elevation changes with the tides. So you can use several different measurements and the changes in elevation in the surface to see which parts are floating and which are not. And then there's a little bit of a transition zone. So there's a little bit of uncertainty, but we have very good constraints on where the grounding line's position is and how it's changing. What we don't have is a very long record, especially for ice sheets. Our satellites haven't been up for very long, and especially the ones that can measure things like the grounding line migrations. And ice sheets are typically very slow to change, even though we have these instabilities that can cause rapid changes. So I think, again, this is where looking at the past is quite interesting, because we can look at very different states of ice sheets using the geological records. Does that answer the question?
So my question is, you mentioned that climate is one of the biggest uncertainties in the model. Why has it taken so long to elaborate with that position? And why, are the groups doing this as well, or is our decision?
More and more. I think. And that's a good question. Why is it taking so long? I think it's because, well, in terms of ice sheets modeling, it's been it's only recently, in the past decades, that we've been able to produce models like bicycles and really have these advances in the numerical modeling techniques that we can simulate those processes. So now that we're at this stage, we can start collaborating with statisticians. Now, climate models been around, and very complex GCMs have been around for longer. And I think there's been a little bit of a reticence to do some work on uncertainties. And we talk a lot about putting error bars on observations, and not so much about putting error bars on models. And this is partly because general circulation models are developed by really a team of climate modelers. They might work on parts of the system, the sea ice, the atmosphere, the ocean. They all try and get the best calibration for their models, and then they put it all together. So it's a very lengthy and complex process to produce just one model that will be right on time for the next IPCC report to run, you know, all the scenarios of future climate change. So it doesn't leave space in this process or time to really look at uncertainty. And there's also a race to have models that have more and more processes in them, or run at higher resolution to better represent the processes. But that doesn't allow us to run ensembles of simulation. So there's a little bit of a different aim, I guess, from the climate modeling community and the really statisticians who would love to collaborate with climatologists. It's starting, but I know the Met Office is still not so keen on collaborating with statisticians to even calibrate their models. So.